Last time we ended on a genuine cliffhanger. We spent a whole conversation watching Maxwell prove that light is a wave, a ripple in the electric and magnetic fields, traveling at the speed his equations demanded. And then, right at the end, you told me that was only half the story. You said light is also a stream of particles, little packets called photons, and that this impossible-sounding double life, wave and particle at the same time, doesn't stop at light. You said it infects all of matter, everything, including me. So today I want to walk through that door. George, what does it actually mean to say a particle is a wave? And what is this thing, the wave function, that everyone says is at the center of quantum mechanics?
Today we go through the door, and I'll warn you kindly at the outset. This is the part of physics where your everyday intuition stops being a reliable guide. Not because the subject is illogical, but because it describes a layer of reality your senses never evolved to touch. But it is completely learnable, and there's a single object at the heart of it that once you hold it, organizes everything. The wave function. So here's our path. First, I'll show you the experiment that forces the strangeness on us, so you can't wriggle out of it, the double slit. Then we'll meet the wave function itself and the rule that connects it to what you actually see, which is due to Born. Then the Schrödinger equation, which is the law that moves the wave function through time. The quantum answer to force equals mass times acceleration. And then the three big payoffs. Superposition, why energy comes in discrete lumps, and the measurement puzzle that physics has genuinely not finished arguing about.
Before the experiment, why would anyone even suspect a bit of matter could be a wave in the first place? Where did that leap come from?
From one of the boldest guesses in the history of physics, and it came straight out of the puzzle we ended on last time. By the early 1920s, physicists had been forced to accept the double life of light. Maxwell's wave, yes, but also Einstein's photons, particles. Light was somehow both, and a young French physicist named Louis de Broglie asked a question of pure, daring symmetry. If waves, light, turn out to also be particles, then why not the reverse? Why shouldn't particles, electrons, matter, turn out to also be waves? He proposed that every particle has a wavelength associated with it, set by its momentum. The more momentum, the shorter the wave. And that formula quietly explains why you've never noticed your own wave nature. For anything as heavy as a baseball, the wavelength that comes out is so unimaginably tiny, far smaller than an atom, that it's utterly undetectable, and the ball behaves like a plain particle. But for something as light as an electron, the wavelength is comparable to the size of an atom, big enough to have visible, dramatic consequences. It was a wild proposal on nothing but symmetry and a formula, and the experiment that put it to the test and proved it staggeringly right is the double slit.
Start with the experiment then, because you said it forces the issue. What's the double slit?
It's the most important experiment in all of quantum mechanics, and its beauty is that it's almost childishly simple to describe. Take a barrier with two narrow parallel slits cut in it, close together. Shine something at the barrier and see what lands on a screen behind it. Now, if you send waves at two slits, water waves or Maxwell's light waves, you get a very characteristic result on the far side called an interference pattern. The waves come through both slits, spread out, and overlap. In some places, a crest from one slit meets a crest from the other, and they add up to a big wave. In other places, a crest meets a trough, and they cancel to nothing. So on the screen you get a striped pattern. Bright bands where the waves reinforced, dark bands where they cancelled. Stripes are the unmistakable fingerprint of waves passing through two openings. Everyone agreed light does this. It's one of the ways we knew light was a wave, long before Maxwell.
Right, waves overlapping and adding up or cancelling out, bright and dark stripes. That's ordinary wave behavior. So where does it get strange?
It gets strange when, instead of light, You fire electrons, little particles of matter, bits of solid stuff, the things that make up the outer parts of atoms. Fire a beam of electrons at the two slits and look at the screen. You get stripes, an interference pattern. The electrons, which you were quite sure were particles, tiny bullets, behave like waves, overlapping and cancelling exactly as water waves do. That alone is a shock, matter interfering with itself. But hold on, because it gets far stranger, and this is the version that should genuinely unsettle you. Turn the beam down until you're firing electrons one at a time. A single, solitary electron, then a long pause, then the next. Each electron, when it hits the screen, lands as a single point. One dot. A tiny flash at one spot. That's a particle. Bullets make dots, waves don't. So each electron arrives as a particle at one definite place.
Okay, so one at a time, each one makes a single dot. That sounds reassuringly like particles again. Bullets, one hole each.
It does, until you wait and let thousands of them go through, one lonely electron at a time, each making its own single dot, and you stand back and look at the accumulated pattern of all those dots. They form stripes. The interference pattern builds itself up, dot by dot, out of thousands of individual particles that each went through completely alone, with no other electron anywhere near it to interfere with. Sit with how impossible that sounds. Each electron travels alone and lands as one particle at one spot, but the collection of where they're allowed to land is dictated by a wave interference pattern, as though each single electron somehow went through both slits at once, interfered with itself, and that self-interference decided the odds of where its one dot would appear.
That can't be right, though. It has to actually go through one slit or the other. Can't you just watch it? Put a little detector at each slit and catch which one it really goes through.
You can, and this is the twist of the knife, the detail that tells you nature is genuinely playing by different rules. You put a detector at the slits to catch which one each electron passes through. And the moment you do, the moment you actually acquire the which slit information, the stripes vanish. The interference pattern disappears completely, and you get a plain, boring blob, exactly what you'd expect from ordinary bullets. So when you don't look, each electron behaves like a wave going through both slits and interfering with itself. The instant you look and force it to declare which slit, it behaves like a particle going through one. The act of finding out which path it took destroys the wave behavior. Nature refuses to let you see both the went through both slits like a wave and the went through one slit like a particle faces at the same time.
That is deeply weird. The watching changes the outcome. So I have to give up the idea that the electron has a definite path at all, unless I measure it.
You have just stated the central lesson of quantum mechanics, and you got there yourself. Before measurement, the electron does not have a single definite position or a single definite path. What it has instead is the thing we've been building toward, a wave function. And here's how to picture it. Instead of the electron being a tiny dot at one location, think of it as described by a wave, a spread-out entity that has some value at every point in space, thick and strong in some regions, thin or zero in others. That wave is the wave function, written with the Greek letter psi. It is not a wave in a material medium the way sound is a wave in air, and it's not Maxwell's electric field either. It's a more abstract thing, a wave of possibility, spread over all the places the particle could be found, whose shape encodes everything nature will let you know about the particle.
A wave of possibility. That's evocative but slippery. If the wave function is spread out all over space, but I always find the electron at one spot as a single dot, how do those two things connect? How do I get from the spread-out wave to the one flash on the screen?
That is exactly the right question, and its answer is one of the most important rules in physics. It's called the Born rule, after Max Born, and it's the bridge between the abstract wave and the concrete click of a detector. The wave function itself, psi, is not directly the thing you measure. You never see psi. What you can see is where the particle shows up. And Born's rule says, take the wave function's size at a given point, how big the wave is there, and square it, and that gives you the probability of finding the particle at that point. Where the wave function is large, the square is large, and you're very likely to find the electron. Where the wave function is small, you're unlikely. Where it's zero, you'll never find it. So the spread-out wave of possibility is quite literally a map of probabilities. Its squared size, region by region, tells you the odds of where your one dot will land.
So the wave function doesn't tell me where the electron is. It tells me the odds of where the electron will be when I check. That feels like a huge retreat from the way physics used to work. I thought physics was supposed to predict what actually happens, not just the betting odds.
You've put your finger on the philosophical earthquake, and it's important not to soften it. Yes, quantum mechanics, at its core, predicts probabilities, not certainties. Fire the identical electron at the identical apparatus 1,000 times, prepared in exactly the same way, and it can land in different places. Physics can tell you the odds for each spot with fantastic precision. The theory is the most accurately tested in all of science, but it cannot tell you where any single electron will go. And here's the part that took even Einstein to his grave uneasy. This is not because we're ignorant of some hidden detail, some secret extra information that would let us predict the exact spot if only we knew it. As far as anyone has been able to establish, the randomness is woven into nature itself. The electron genuinely does not carry a predetermined answer. The universe, at bottom, appears to deal in probabilities. Einstein hated this. God does not play dice, he said, but the experiments have sided, over and over, with the dice.
Is position the only thing that goes fuzzy like this? Or does treating the particle as a wave make other things uncertain too?
It spreads to more than position, and this is where one of the most famous ideas in all of physics falls out almost for free, Heisenberg's uncertainty principle. And I want to show you that it's not the mystical thing people make it out to be. It's a plain fact about waves. Think about what it takes to make a wave that's sharply localized. A wave function that's a tall, narrow spike at one spot, so the particle has a very definite position. To build a spike like that out of waves, you have to add together many different wavelengths. A single pure wavelength is spread out evenly everywhere, so it takes a whole pile of them, overlapping, to pile up at one point and cancel everywhere else. But remember de Broglie, wavelength is momentum. So a wave function with a sharp position is necessarily made of many wavelengths, which means many momenta. Its momentum is wildly uncertain. And the reverse, a wave function with one pure wavelength has a perfectly definite momentum, but that wave is spread out over all of space, so its position is completely uncertain. You cannot make a wave that is both sharply peaked in position and made of a single wavelength. It's impossible, not practically, but mathematically.
So the uncertainty isn't about my measuring equipment being clumsy and disturbing the particle. It's that a wave sharp in one thing is inherently blurry in the other.
Precisely, and that distinction is everything. It is not that we bump the particle when we look, though that's the story often told. It is that the particle genuinely does not possess a sharp position and a sharp momentum at the same time, because it is a wave, and no wave can be sharp in both at once. There's a lovely everyday echo of the same mathematics in sound. A very short click, a sound sharply located in time, has no definite pitch. You can't say what note a click is. And a pure, definite musical note must be sustained for a long time. The instant you demand an exact pitch, the sound must spread out in time. Sharp in time, blurry in pitch. Sharp in pitch, blurry in time. The identical trade-off. Position and momentum are a package deal in exactly the same way, and Heisenberg's principle just names the price. It's a direct consequence of the wave nature we've been building, not an extra mysterious postulate bolted on.
All right, I'll accept the wave of possibility and the squaring rule for the odds, but a wave has to do something over time. It has to move, evolve, change shape. What governs how the wave function changes? You said there's an equation that's the quantum version of force equals mass times acceleration.
There is, and it's the crown of the whole subject. The Schrödinger equation, written down by Erwin Schrödinger in the 1920s. Think back to our very first tutorials. Newton gave us force equals mass times acceleration, a law that takes where a particle is and how it's moving now and tells you where it'll be an instant later. The Schrödinger equation plays exactly that role, but for the wave function. You hand it the shape of the wave function now, and it tells you the shape of the wave function an instant later. It marches psi forward through time. Feed it the wave function today, and it grinds out the wave function tomorrow, smoothly, continuously, with no randomness at all in that marching.
Wait, stop. No randomness? You just spent 10 minutes convincing me the whole point of quantum mechanics is that it's random. Now you're telling me the master equation has no randomness in it.
This is the single most important subtlety in all of quantum mechanics, and almost everyone gets it muddled the first time. So let's be very careful and very clear. There are two completely different things going on, and you must keep them apart. Thing 1. How the wave function evolves when you're not measuring it. That evolution, governed by the Schrödinger equation, is perfectly deterministic and smooth. The wave of possibility flows, spreads, and reshapes itself in a fully predictable way. If you know psi now, the equation tells you psi later with total certainty. No dice at all. Thing 2. What happens when you make a measurement? That is where the randomness lives. The Born rule kicks in, the squared wave function gives you odds, and nature rolls the dice to pick one actual result. So the wave function evolves with complete predictability right up until you look, and only the act of looking introduces the randomness. Predictable wave, random measurement. Hold those two apart, and half the fog of quantum mechanics lifts.
That genuinely helps. The wave itself flows predictably. The randomness only bites when I measure. Okay, what's actually in the Schrödinger equation? Can you tell me in words what it says without writing symbols?
I can, and there's a lovely thread back to our earliest episodes hiding inside it. The equation says, in essence, that the rate at which the wave function changes in time is governed by the energy of the system. On one side, you have how psi is changing moment to moment. On the other side sits the total energy, the kinetic energy of motion plus the potential energy of position. And that total energy object has a name we've met before, the Hamiltonian, from our tutorials on least action, where it came out as the total energy of a system. It's the very same Hamiltonian now promoted to run the quantum world. So the deep structure is, the total energy drives the evolution of the wave function. The thread we started pulling with Lagrange and least action through the Hamiltonian runs all the way here into the equation at the heart of the quantum. Energy is what tells the wave of possibility how to move.
One thing still nags me. You keep calling psi a wave, but a water wave has an obvious up and down, a height that rises and falls. What is the wave function's version of up and down? What is actually waving?
This is a subtle and important point, and getting it right is what makes the double slit finally click. The wave function, at each point in space, has two pieces of information, not one: a size and a phase. Picture a tiny clock hand at every point, a little arrow that has both a length and a direction it's pointing. The length of the arrow is the size of the wave function, and when you square it, you get the probability, as Born told us. But the direction the little clock hand points, the phase, is the second, hidden piece, and it's invisible to any single measurement of position. So why does it matter? Because when two parts of a wave function meet, say the piece that came through the left slit and the piece that came through the right, what decides whether they reinforce or cancel is whether their clock hands are pointing the same way or opposite ways. Aligned arrows add up into a bright fringe. Opposed arrows cancel into a dark one. That rotating phase, the direction of the little clock hand, is the entire machinery of interference.
So the phase is the thing that's secretly waving, the clock hand turning, and even though I can never see it directly, it's what makes the stripes appear.
Exactly. And that's why the wave function has to be described by a richer kind of number than an ordinary quantity, a number that carries both a magnitude and an angle, which mathematicians call a complex number. People sometimes hear complex numbers and assume it's just calculational bookkeeping, but here it's physical. The extra ingredient, the phase angle, is precisely what allows two possibilities to interfere and cancel. Strip the phase away and leave only the sizes, and interference becomes impossible. The double slit would give a dull blob, and there would be no quantum mechanics as we know it. So when I say psi is a wave, I mean it has this turning phase, this clock hand, sweeping around as the wave moves through space and time. The height that rises and falls is the turning of that hidden arrow.
I love that the least action thread reaches all the way into quantum mechanics, and now the wave has a real texture for me. You promised 3 payoffs. The first was superposition. What is it?
Superposition is the direct consequence of psi being a wave, and it's the feature that makes quantum mechanics so powerful and so strange. Waves add. If one wave function describes an electron being here and another describes it being there, then their sum, a wave function that is here and there at once, is also a perfectly valid state the electron can be in. The electron can be in a combination, a superposition, of here and there simultaneously, not because we're unsure which one it's in, but because being in both at once is a genuine physical state. That's what the single electron in the double slit was doing. Its wave function went through both slits, a superposition of through the left and through the right, and the two parts interfered. And when you finally measure, the superposition of many possibilities collapses to the one you happen to find, with the odds set by Born's rule. Superposition is why a quantum computer can, in a sense, explore many possibilities at once. It holds them in superposition, and it's the sharpest break from the classical world, where a thing is only ever in one state at a time.
So superposition is just waves add, taken completely seriously, applied to the wave of possibility. The second payoff you promised was the one I'm most curious about. You said this explains why energy comes in discrete lumps, why it's called quantum at all.
This is my favorite part, because it's where the abstraction suddenly explains something you can see with your own eyes, and the analogy that unlocks it is a musical instrument. Think about a guitar string, fixed at both ends. You can't make it vibrate any old way, because it's pinned down at both ends, only certain patterns fit. The fundamental, where the whole string swings as one arch, then the pattern with one still point in the middle, then 2 still points, and so on. A whole number of half waves has to fit neatly between the fixed ends. You get a discrete ladder of allowed vibration patterns, which is exactly why a string plays specific musical notes and not a continuous smear of pitch. The in-between patterns simply don't fit. They'd have to move at the pinned ends, which they can't. Now here is the quantum leap. Take an electron and confine it. Trap it, say, inside an atom, bound to the nucleus. Its wave function is now a wave confined to a small region, and just like the guitar string, only certain standing wave patterns fit in that confinement. The in-between ones don't. And since, by the Schrödinger equation, each allowed pattern corresponds to a particular energy, only certain discrete energies are allowed. The electron cannot have just any energy, it can only occupy the specific rungs of an energy ladder set by which wave patterns fit.
So the discreteness, the quantum in quantum mechanics, is literally the same reason a guitar string plays distinct notes. Confine a wave and only certain patterns, certain energies, fit.
Precisely, and this is one of the great explanatory triumphs in the history of science. Before quantum mechanics, it was a brute mystery why atoms emit only specific, sharp colors of light. Every element has its own fixed set, like a barcode, a signature of exact colors and no others. Heat sodium and it glows a specific yellow. Hydrogen glows specific reds and blues. Nobody knew why. The wave function answers it completely. The electron in the atom can only sit on the discrete rungs of its energy ladder, the allowed standing wave patterns. When it drops from a higher rung to a lower one, it releases exactly the energy difference between those two rungs as a single photon, and that precise energy corresponds to a precise color. The barcode of colors from each element is a direct readout of that element's ladder of allowed wave patterns. The lumpiness of the atomic world, the quantum, is the wave nature of matter, forced into standing waves by confinement. Colors from a flame are the atom singing its allowed notes.
That is genuinely beautiful. The colors of a flame test are an atom playing its allowed notes. Before the third payoff, though, is there some other consequence of matter being a wave that actually shows up in the world? Something I'd never have guessed from thinking of particles as little dots.
There's a spectacular one, and it powers the sun, so it's hard to overstate. It's called quantum tunneling. Here's the idea. Because a particle is a spread-out wave, its wave function doesn't stop dead at a wall. Imagine a barrier the particle classically hasn't got enough energy to cross. Think of a ball that can't roll over a hill because it lacks the energy to reach the top. A classical particle simply turns back every time. But the wave function doesn't turn back sharply at the barrier. It leaks into it, dropping off but not instantly vanishing. And if the barrier is thin enough, a little bit of the wave is still non-zero on the far side. By Born's rule, a non-zero wave function beyond the barrier means a real, if small, probability of finding the particle there. On the other side of a wall, it never had the energy to climb. The particle can pass through the hill without going over it.
A particle getting to the other side of a wall it can't climb over. That sounds like cheating. And you're saying this actually happens out in the real world?
Constantly, and your life depends on it. Start with the sun. The sun shines because hydrogen nuclei, protons, fuse together in its core, releasing energy. But protons are all positively charged, and like charges repel ferociously. At the temperatures even in the sun's core, protons don't actually have enough energy to overcome that repulsion and touch. By the classical rules, the sun couldn't burn. It burns because the protons tunnel. Their wave functions leak through the barrier of repulsion, and just often enough, two find each other on the far side and fuse. Sunlight is quantum tunneling made visible. And it's everywhere else too. Certain kinds of radioactive decay are a particle tunneling out of a nucleus that classically should have trapped it forever. And we've built devices on it. A scanning tunneling microscope images individual atoms by measuring electrons tunneling across a tiny gap. And the flash memory in your phone traps and releases charge by tunneling. A particle passing through a wall it cannot climb. There is no way to picture that with little dots. It is pure wave function, and it lights the sky.
The sun shines because of a quantum trick. That reframes the whole daytime. All right, the third payoff was the one you flagged as unfinished business. The measurement problem. What's unresolved?
Here I have to be candid with you, because it's a place where physics is still genuinely arguing, and pretending otherwise would be a disservice. We have two rules for the wave function that don't obviously fit together. Rule 1, the Schrödinger equation. Between measurements, the wave function evolves smoothly, deterministically, spreading into superpositions, here and there at once. Rule 2, measurement. When you look, you never see a superposition. You see one definite outcome, one spot, one result, and the wave function seems to abruptly collapse from a spread-out wave of many possibilities down to the single one you found. The trouble is that these two rules are utterly different in character. One smooth and deterministic, the other abrupt and random, and nothing in the theory cleanly says when or why or how the switch from one to the other happens. What counts as a measurement? What is special about looking? Why this jump?
And physics just doesn't have the answer to that?
Not an agreed one, no. And it's one of the deepest open questions in the foundations of the subject. What physics has instead is a set of competing interpretations, different stories about what's really going on, all of which reproduce the same experimental predictions, so no experiment has yet cleanly settled between them. One school, historically called the Copenhagen interpretation, essentially says, don't ask. The wave function is a tool for computing odds. Measurement causes collapse, and that's where the story stops. Another, the many worlds interpretation, takes the Schrödinger equation utterly at its word, says the collapse never really happens, and instead every possible outcome occurs, each in its own branch of a constantly splitting universe, so there's a version of the world for every result. And there are others still. I'm not going to tell you which is right, because nobody really knows. What I want you to take away is that the mathematics of quantum mechanics is crystal clear and works with unbelievable precision. But what it means, what's actually happening when a measurement occurs, remains beautifully, stubbornly unsettled.
I actually appreciate that you won't pretend it's solved. So let me try to gather the whole arc, and you catch me where I slip. We came in from Maxwell's cliffhanger. Light is wave and particle, and so is matter. The double-slit proves it. Electrons build up a wave interference pattern, one particle at a time, but only if you don't peek at which slit. So a particle is described not by a position, but by a wave function, psi, a spread-out wave of possibility, and the square of its size gives the probability of finding the particle at each place. That's Born's rule, and it means physics predicts odds, not certainties. The Schrödinger equation marches the wave function through time, smoothly and deterministically. The randomness enters only at measurement. And out of this comes superposition. Waves add, so a particle can be in many states at once. Quantization. Confine the wave and only certain standing patterns, certain energies fit, which is why atoms have discrete energy levels and sharp colors. And the still unsolved measurement problem.
That is the whole arc, captured cleanly, and the single sentence I'd want you to carry is this. In quantum mechanics, a particle is not a tiny dot with a definite position, but a spread-out wave of possibility whose squared size gives the odds of what you'll find. And confining that wave is what forces the lumpy, quantized, barcode of colors world we actually live in. Newton's certainty about where things are gave way to Schrödinger's wave of what might be. And it is not woolliness or hand-waving, it is the most precisely confirmed framework in the history of physics. The strangeness is real, and so is the accuracy.
From where is the particle to what is the shape of its wave of possibility, that's the shift. And I have a feeling you're about to tell me there's something even stranger waiting. You have that tone.
I do, because there's one more quantum property that outdoes everything we've discussed today for sheer strangeness. Precisely because it has no analogy in the everyday world at all. No spread-out wave you can picture, nothing to point to. It's called spin. Every electron carries it. It behaves in some ways like the electron is rotating, and yet it absolutely is not a tiny spinning ball. It's a genuinely new kind of quantity with no classical picture whatsoever. And the experiment that revealed it is one of the most elegant in all of physics. You send atoms through a specially shaped magnetic field, and instead of spreading into a smear, they split into two sharp, separate spots, as if this hidden property can only ever point fully up or fully down, never anywhere in between. That's the Stern-Gerlach experiment, and it's where we go next. Spin, the most purely quantum thing there is. For now, carry this: matter is a wave of possibility, and confining that wave is what makes the world lumpy, discrete, and full of the sharp, specific colors we see.
Spin, a rotation that isn't a rotation, splitting atoms into two clean spots. I'll be turning that over all week. Thank you, George. Next time, spin and Stern-Gerlach. For now, the particle is a wave of possibility, the square of its size is the odds, and confinement is why the universe comes in lumps.